You will record it, yeah? It's okay. No, I just wanted to.
We have хотела распределение, я хотела распределить голос. Зачем? Скажи, я можно писать.
Да, она мне показала, все знаю.
Yeah. Oh, look at this. I'm not.
Okay, welcome PCS members and friends to our today's PCS IBS seminar. It is a great pleasure to have with us today Professor Viktor Kagalovsky from Shamon College of Engineering, Israel. And our scientific host today is Sergey, who will introduce our speaker. Please.
Yeah. Okay, thank you. Welcome everyone and to our PCS seminar in hybrid mode. Welcome to Zoom guests. Today our speaker is Viktor Kagalovsky, and many of us already know him, but for those who don't, I will reiterate that first of all, he's a frequent visitor to PCS, and not only, but also to the PKS in Dresden, as I just checked from a long list of his visits from the last 10 or so years. Let's see. So Viktor studied physics in Kharkov at the Polytechnical Institute in Kharkov, and then he had some intermediate postgraduate experience in the Institute of Physics in Krasnoyarsk, and then he moved to Israel, did his PhD at the Ben Gurion University in Be'er Sheva with his supervisors Horowitz and Avishai. And then he moved on for a postdoc stay in the group of Hans Weidenmüller, whom we discussed already very intensively during the last couple of days. And then he moved back to Israel and first to the Ben Gurion University, and then he moved to the Shamon College of Engineering since 2004, where he rose through the ranks and is now the head of the Department of Electrical Engineering and a full professor. He has a number of highly cited publications. His research is in condensed matter physics, and maybe it's best if I tell you what the topics of the advanced study groups were, which he convenes at our center, and then you get an idea about also his research interests: quantum phase transitions, quantum Hall systems, topological insulators, Anderson localization, Lagrangian physics. He also organized with others 2 workshops at our center in 2018 and 2016, again in the broad field of these topics, which I already mentioned. And today we will speak about fractional conductances in the strongly impacting money systems. So please, the floor is yours. Let's welcome our speaker.
Thank you very much, Sergey, first of all, for propagating me through the whole of my life, and just a strange feeling. It's always a pleasure to come here, and I want to thank Sergey for these opportunities, because the atmosphere in this place, and he mentioned also Dresden, this is a place where you can make research and enjoy collaboration, and a lot of our research was done here, and part of my talk today was also advanced strongly last summer when we, together with my friend and collaborator Igor Yurkevich, were visiting together, and he will come later. I was actually, as usual, I start with connecting 2 pictures, the place where I'm staying right now and unknown flying object of my college, which is probably now the most famous photo from Be'er Sheva. And I was actually supposed to give a talk about already the work was being almost finished, and it will be published with one of the affiliations, obviously PCS, IBS, out of question. But it turns out that it's actually in such a progress that I hope maybe when Igor comes in a couple of months, he will tell you more about this. So I'll talk only about particular subject of fractional conductance, but it looks like we can actually cover more. So what I'm going to talk about is to present you one of the best experiments of the recent years by the group of Mike Pepper, which found in non-magnetic fractional quantization, which was completely unexpected because usually you have fractions in fractional quantum Hall effect, which is called fractional. It was done without magnetic field, and the variety of the numbers definitely demanded some explanations. I'll mention and talk about the application, how Lagrangian liquid one-dimensional description can describe when you have leads far away from your sample. Then I'll talk about relevant perturbations actually it's not in two-channel, I don't know what is written two-channel, in many-channel one-dimensional system. Then I'll speak about I'll start with two-channel, it's correct. Then I'll talk about what is the number of channels and number of perturbations and how you can deal, how perturbations can coexist. Can they act on your sample together? Then, in my opinion, probably the most amazing part is even denominators, because in fractional quantum Hall effect, all denominators are odd numbers. And here it was observed and needed explanation. The even denominators, and hopefully I conclude. So, first of all, this is a permanent. I'm sorry for this. I didn't expect that the picture will be. This is the picture from the Pepper group. First, they were measuring one-dimensional systems, which were made with gallium arsenide and aluminum samples, where they were able to change the confinement potential, meaning that they can change how wide is the propagation of current in your case. So in some sense, change the number of channels. So it's really a multi-channel one-dimensional system. And first, they actually got huge number of fractions, almost, I mean, not everything is infinite, but huge. Then they were very accurate at checking that they can observe plateaus, and these are the most important numbers. Sorry for the quality. So for the most important is 1/2, which is absolutely, this is very famous. One half, you don't have flutter in quantum Hall effect. This is a transition between two flutters. Then 2/5 is a normal number, and 1/6, another one. Obviously, 1 is just one channel conductance. And so, how can we think about this problem at all?
Sorry,
Yes.
can I ask?
Yes, sure.
Short question. In this experiment, how can you distinguish the number of channels in the transmission?
The answer is no.
Yeah, the thing is that from the experimental data, how do you know that the number of channels?
They don't know,
Yeah.
and we hope that maybe I'll show you one at the very end. I'll show you one of the additional results, which probably speaks about the number of channels. But believe me, we're talking with Mike Pepper and asking him, and he also doesn't know, but hopefully one day. So, even denominator, this is the main message of my talk. And it turns out that it is related, immediately the description is related to one-dimensional Lagrangian, but because the sample of Pepper, the samples of Pepper group were very clean, and the electrons were attached far away, so the measurements were actually done on the theoretical level at infinity. This means that this seminal work by Maslov and Stone immediately is applicable. And this work tells you that, okay, you are in the with Lagrangian liquid. With Lagrangian liquid, you know there is a Lagrangian parameter which describes it. It tells you if the interactions are repulsive or attractive. If this is number, people were trying to explain fractional quantum Hall effect with the help of Lagrangian liquid, were saying that Lagrangian parameter is simply the fractional Hall conductance. But this work tells you that if you are attached very far away to a two-dimensional Fermi electrodes, which are not one-dimensional, the Lagrangian parameter is 1. And those guys have proven that the answer for such a system, it doesn't matter how strongly interactive the system is, if you measure far away, the answer is just E squared over H. Nothing related to K at all. And this gives you a sort, so how it is possible to explain. And this first approach was done in a very good work by Shavit and Oreg, who said the following: let us consider two channels and suppose there is a relevant perturbation. In this case, in their particular case, they're talking only about backscattering. Backscattering localizes something. When backscattering, if backscattering localizes one of the channels, the second channel is conducting with value 1. But if the perturbation is more complicated, it can localize some part of your system. The remaining part will give you some conductance. And the idea was the following, that if the perturbation is described by this cosine, and you know that perturbation is relevant when the scaling dimension is below critical, and as you decrease the temperature of the system, this perturbation becomes more and more important. And I will show you exactly what this perturbation means on the language of phi1 and phi2 are bosonic fields which describe first and second channels. And N1 and N2 are telling you how many particles are being backscattered in each channel. Then they have shown that this corresponding field, which will be frozen. And then what else? If you started with two channels, with phi1 and phi2, you are now have frozen part of it. The part perpendicular to it will remain free. If this contribution of this remaining part is something, and this is what they have shown. These are two integer numbers. So if in the first channel N1 particles were scattered, and in second N2, this will be the answer for the conductance. And it turns out that it immediately gives you one of the numbers on this experiment. Just take 3 and 1, and you immediately obtain 2 over 5. Okay, so when we are thinking about it and we are working with the multi-channel Lagrangian liquids for a long time, first question was, what about even denominator? And what I'm presenting next 2 slides is on the level of the 3rd grade, not of the university, the 3rd grade of the basic school. But by some reason, I still don't understand. Maybe someone tells me what it should be some theorem. It's impossible that it is very easy. I asked my son who is doing math now, and we still didn't find anything. So please have a look. So this is one perturbation. When you have a system of n channels and you are describing perturbation by n1 particles in the first channel, n2 particles in the second, and so on and so forth, this is the result. This is the result presented in this Shavit paper. And I am asking the question, so what do I need that after cancellation, I will have even denominator? Let's play. So first is their result. How can I hope for the even denominator? I can ask to put here both numbers which are even.
There's a minus missing here?
No, this is already after the, yes, this is exactly what I told when I was copying. I'm sorry, this is from the Israeli laptop. So you see that if you substitute 2, it is cancelled, so you have to continue. So it will continue until they stop being even. So what do you need to have even denominator? You want both of these numbers to be odd. Is it okay? It's clear. Let us substitute. This is what we are doing. And you see that we are obtaining even plus 1. This is an odd number. So I never can have in this expression, I will never have even. Okay, let's do 3. So I'm talking about one perturbation, which mixes me all 3 channels. So once again, let us substitute even numbers because I want even denominator, and I hope that it will win against the numerator after cancellation. Nothing good, nothing. The same cancellation. So I can put here 2 odd numbers, which will give me even, and 1 even. Let's do it. Even plus 1 doesn't work. Now 4 numbers. I can put 2. Okay, so you understand that I don't need to put all 4 of them even because they will cancel each other. And you continue. So I put 2 of them even. So all even, nothing interesting. 2 even. I'm going back to this page. Nothing. So I put all 4 of them odd. And this is a nice exercise, really, maybe not even for the second grade. You know that the product of 2 consecutive numbers is always even. So even, plus 1, you still have odd. I'm almost gave up. It was actually done in this room half a year ago, so I tried 5. So in this case, you hope to put 4 of them odd and 1 even. And it turns out in an incredible way that if this guy is odd plus 1 will be even, it will be finally not cancelled. And sometimes when we're doing nothing related to this work, but sometimes when we are trying to describe topological insulators and using some matrices, which I will talk about later, we were accused of some kind of fine-tuning that you just find good numbers. Now we check. 4 channels didn't work, so 5 channels. What would be the first number which you suggest? We're talking about particles being backscattered. So I obviously don't want too many particles. So the easiest number would be 0, 0, 0, 1. Which is normal, because if I take all of zeros, it's once again. And it turns out that if I take these numbers, it means 1 particle being backscattered in first channel, second channel, third channel, fourth channel, and I need 2 particles to be backscattered in the 5th channel, because otherwise I will not get it. And in this case, I finally understand that I will get finally some even denominator. But what a surprise! This even denominator was exactly the most important result of the experiment. It gives a hope. It doesn't tell you that you have 5 channels, but at least it gave us some idea that it should work. And so we decided to use all our knowledge that we can to describe many particle, many channel system, because as you have seen, in this paper, it was suggested first for 2 channels, 1 perturbation, and then for n channels, still 1 perturbation. We wanted to speak about more perturbations, and more than that, when you describe a system, you can actually allow channels to interact. In this case, it's already not a Lagrangian liquid. It's a sliding Lagrangian liquid. It is more complicated to describe, and I will tell you a few words. So this
maybe just for the sake of understanding in the general public, when you say, let's say, in 1 channel, 1 particle is backscattered, what does it mean compared Relative to what? Relative to how many particles which can go through, or is this a completely blocked channel? What
No, you have a channel.
Yes.
And particle, you start usually with conducting channels.
Yeah.
Then if you introduce some kind of perturbation, like barrier, and if this barrier,
It's kind of like one backscatter.
one backscatter, yeah,
Bent on the entire length of.
no, it's very nice. You can speak about point impurities. In this case, it will be what you said.
Okay.
Or you can speak about that you have disorder, but in this particular case, Pepper was underlying all the time that they have very clean samples. So you can think probably about something like point. And this is very important in order to realize if your perturbation is relevant or not, because the scaling dimension of point impurity and prolongated disorder are different. You compare it with different numbers.
There's many body localization moving around here.
Somewhere, yes, because I mean, this is
Or
strongly.
it's a weak disorder. Can we say it like this?
And I'm not sure that I can say it because I mean, obviously it starts with weak disorder, but as you decrease temperature, or if you are talking about RG, if it's relevant, it becomes stronger and stronger. It's a good question. Because we're talking about description of the language of channels, and if the disorder is relevant, some channels become localized, gapped. Okay, so this is a description of multi-channel Lagrangian liquid. What is the difference with the usual one-channel Lagrangian liquid? Now, these are the matrices which describe density-density interactions and current-current interactions. And because of this, you cannot arrive to a single parameter K, which is the description of Lagrangian liquid usually. You need to describe it with the language of the matrix K. This was done by Igor something like 10 years ago. He developed it, and we are trying to solve this in various cases with different density and current interactions. If you have multi-channel, you can say that only neighbors are interacting, or you can say in topological insulators that everyone talks to everyone. It's really a big problem, and we were trying to solve it each time, and we were lucky to solve it until finally we found some very unknown paper in mathematical journal which showed us that this problem is solvable always. This is its solution, and this is nice exercise already, not for the third grade of school, but for the third grade of the university. If you substitute this guy here, you will immediately solve it. And this is really was a pleasure, and I'd like to cite this paper, which was written in some unknown journal, but by some mathematicians, and this is really a pleasure was when Igor found it. Okay, so now the question is, can we apply Maslov-Stone approach and say that it doesn't matter what our K matrix is, as long as I am measuring at the infinity, it is matrix 1. So I am back to the idea of Shavit and Oreg, and I am checking what is being kept or not. This is all. It was not a trivial question, because what Maslov and Stone have done for one channel, they have solved a perturbation theory for the Green's function. It was a very nice result. And because when you calculate conductance with the help of Cuba formula, you multiply this Fourier transform of Green function by omega, what you are interested in is the first term, because it tells you what is your DC limit omega goes to 0 conductance. And it was really a pleasure to solve it. And we obtained exactly the same result as Maslov and Stone. But Maslov and Stone have got this just a number K. We have got our matrix K, which is any solution here. And so when we reproduced their results on the language of the matrices, it was clear to us that we can speak that if we describe relevant perturbations which are getting localizing part of our system, then the rest will conduct. And so K finally will be substituted 1, which is matrix 1. So this was the idea. This is the formula which was used by, once again, this is generalization of Maslow's-Stone formula. And you can check that because this Green's function is just the correlator of these bosonic fields, it turns out that all you need to do is the following. So you have a system. Obviously, you describe it with on the language of bosonic field for each channel. Then you say, I have a perturbation. 1, 2, 3. We'll speak about the how they can coexist or collaborate. And then if those perturbations are relevant, you say the following. I will change the basis of description of my system. I go to the new basis. Part of this new basis will be my perturbations, which I will call new fields. Those new fields will be gapped. And after they will be gapped, I will throw them away. And I will remain with the remaining conducted fields. And this is the approach, and this is work. So you start with original. This is vector, which is just bosonic field in first channel, second channel, and so on. And you write it down on the language of the new basis you knew. And then part of this, guys, and this is just the definition of the vector, which is useful for calculations because we need to calculate this stuff. And then what is you are doing? You are substituting this formula here. You need summation like this. So this is why I'm using this E vector. And you finally obtain the following, that your conductance, which is the definition, this is exact definition. But after part of these guys becomes gapped, you throw them away. So you need to calculate only 3 channels in your new basis. And that's it. This is the definition. So you can either calculate 3 channels. This is a projector to 3 channels subspace. Or you can make 1 minus gapped channels, which is, it's up to you what is better for you to do. Obviously, when you have 2 channels, you have either this one, also the second, and they're exactly the same. So this was the result. And this result obviously reproduces what I have shown you from the paper by Shamit. And this is,
The some indices, the mu raised integer in your calculation.
No, but here mu is just the number of new channels. So this obviously it's the integers.
Yes, that's why I'm interested.
Yes.
The number of new channels for raised integer.
Yes, absolutely, very nice. It's the number of new channels is integer. The contribution of a channel will be some fraction. Where you are getting that you are getting this vector u will give you, when it is multiplied by the vector, which is just all numbers 1, will give you fractions. This is the point. Nice. Okay, so first of all, but now after this n equal to 5, our first small contribution was, so what do? We are still working on the language of Shavit paper, which tells us that the perturbations are described only by the bosonic field pi. And I remind you that on the language of Lagrangian liquid, you have 2 fields conjugate, like you have coordinate and momentum conjugate, you have pi and theta. So if you have pi, you have only particular perturbations being described, and this I'll show you. So if I'm still only in this language, but now I want to talk about more than one perturbation, how should I address it? And it turns out that you need description. So first of all, you see immediately that you cannot live only with phi. You also need theta, because right moving particle is described by this operator. This is left moving particle. So obviously we realize that the most general way to describe perturbation is to have phi's and thetas in all channels, and then you can describe anything you want. If you don't have this guy, this is the description used in Shavit paper, you still describe some of perturbations, but not all of them, and I'll speak about this in detail. So if you have only phi I, you just can see immediately how you can get rid of theta. You multiply R cross creation operator by L annihilation operator. So the description suggested in that paper was that you can describe any number of particles being backscattered in each channel individually. So no scattering between channels. Number of particles in the first channel, second channel, and third channel. This is what you get, and this is intra-channel perturbations, and this is very nice. And if you have only intra-channel perturbations, you need to ask a question. If I have a number of perturbations, maybe some of them contribute the same. You are not calculating twice. If you have perturbation N1 phi 1 plus N2 phi 2 and 5 N1 phi 1, 5 plus 5 N2 phi 2, you realize that this is the same because you need only a normalized vector, a unit vector. So you have to get rid of the perturbations which cannot work together. And it turns out that if, this is trivial definition, if these are orthogonal, then you can write down, and this is our generalization of the formula which they presented, that now you can take the number of channels and you take away the contribution stolen by all gap channels under the, if all original perturbations were orthogonal. If not, you go to the first grade of the university and you do Gram-Schmidt procedure. And this is very easy, and there is nothing to discuss here. So we just normalized all the perturbations original and then wanted to show you some nice pictures. So this is a projection operators. And if I do it like this, I continue to the infinity, and I can build any Gram-Schmidt orthonormalized basis. And this will be my final result, which is very nice to present and talk, but you understand that actually you are doing it by hand every time. That's it. So this was, and this is okay, and this is good. And now, and I will use it for sure, because I want to talk about all the numbers which were observed in the experiment. But for now, it was enough. We wanted to ask a question. We are not discussing, and nobody discussed it. In order the perturbation to become relevant, it has to be below its scaling dimension, the parameter which is responsible how it behaves with temperature going down. It has to be below critical number. If we are talking about single impurity, the critical number is 1. If we are talking about disorder, it is number 2. But anyway, if you calculate it, it turns out that usually your perturbations it depends on the number of particles. And if for a single particle, the perturbation really can be reasonable, but already for 2, 3, and 4, this scaling dimension becomes huge. And if it's huge, it is always above critical value, and it is not relevant. So we were a little bit afraid, and I have shown you that I need 5 channels. So I needed 6 particles to get this 1/2. So we were starting to think, is it possible that maybe we will have perturbations between the channels? So we will use the language of phi and theta together, and maybe it will give us perturbation which is relevant at much less critical conditions, but still will produce us with it. And originally, okay, it was interesting, and I'll show you, and then I'll honestly tell you that it's not the final answer. So if I want to talk about perturbations on the most general language, what do I demand? As I told you, if perturbation is relevant, I want it to become my new field, because I will get it and throw it away. So in this case, what I need is that this expression will describe field. What is field? One of the conditions, field has to commute with itself. But when it is built by phi and theta are conjugate. They do not commute. So we have to take care that they do commute. So first condition, that in order to be field, J, Q, scalar multiplication should be 0. This is point number 1. Second, you describe real physics. Real physics tells you that the number of annihilation and creation operators has to be equal. You have particle being scattered from this position to that position, 1, 1. In this case, this is our neutrality condition. This is number 2. They are all satisfied, it's okay. But then you come to the most important point, because this is the citation of the very big person, and you tell the following: when I change the basis, I want my Hamiltonian or my Lagrangian to look the same. What is the first term in my Lagrangian? It is P times Q dot. You can call it kinetic one. And then if you check it, how it is written on the language of Lagrangian, it turns out that you obtain that in order that two different perturbations, when you change the basis, go this in a normal way, you need Haldane criterion. And this tells you that in order for two perturbations to coexist, this is his definition, the two perturbations can affect your system independently only under this condition. So these three conditions are necessary if we want to describe the effect of the system of this perturbation. We demand these three conditions, and we can do it. And then when we have it, we start checking how we can work with them. And it turns out that you can check it from on the very basic. Let's say that we have two perturbations. So let's talk that we have, if we have two perturbations which collaborate and you have two channels, they will kill you. Two channels. So you need three channels, two perturbations. Otherwise, it doesn't work. So it turns out that obviously they have to satisfy this and that. They also, so how do I define them? I already checked that I need these unit vectors, but now they are being normalized by different way. You see that I divided by Q1 squared. It gave us some hope that maybe we will have expressions which provide us with more answers than expressions with N1, N2, and 3. And now we have N to describe J, and we have M numbers to describe Q. It didn't work out, but I'll show you why. Second, let us suppose that this and this, maybe this is wrong, but I'll still talk about it like one of the results. If these perturbations are not orthogonal to each other, I want to know how do they contribute, how one steals something, what part being stolen by the second perturbation. So this was a suggestion. It's kind of Gram-Schmidt. It's not Gram-Schmidt. Gram-Schmidt is defined when you have vectors which live in the same space. Now I have two vectors, J and Q, and hope was that this is the correct procedure. You can check that now U2 times U1 plus V2 times V1 will be indeed 0. So I rotate the basis, and then the answer is interesting, because you see the answer is exactly the same as it was on the language of the fields pi. But what is interesting now? Now the integer numbers which are entering my vector U1 are not just belong to J, they also belong to Q. So First hope was that we are covering more answers that were covered by Shavit paper. And as honest persons, we needed to check. How can I check? Once again, it's different stories. When I'm speaking on the language of phi and theta, I am including not only intra-channel backscattering or something else, but also inter-channel. The language of Shavit paper was only intra-channel. So I was asking if I can somehow to come back to his answers, and the answer is yes. But how? First of all, one more thing. When we are talking on the language of pi, you have n1, n2, and 3 integer numbers. This is the number of particles being backscattered. When you are talking on the language of phi and theta, both j and q have components. These components maybe are both integer or both half integer. This is a very important difference. So they can be 1/2, not just one. And this originally gave some hope. But after, when I calculate the final result, I am working with this normalized vector. So I wanted to check. You understand that if I'm working with normalized vector, I can multiply the upper part and the numerator as a denominator by any huge integer number as I wish to check. So this is what we are doing. So if we can go back just to dependence on phi. And you see what is going on. So these are maybe half integers, maybe. So I want to be sure that they are all integers. How I can do it? First of all, E times Q1, remember this is 0 because of neutrality condition, annihilation, creation. So I can add anything I will. Second, you remember that J times Q is 0 because this is field. So I can add. So I do the following. Now, because J plus Q, even if they are both half integers, the sum is integer. I have this, what I called J1 integer, and this is the result. So the part stolen by the first perturbation, even if I started on the language of phi and theta, the part of the first perturbation comes back just to integer numbers, exactly as it was done in the paper by Shavit and Owen. Okay. What about E2? In this case, I am playing games here, and I am multiplying and adding numbers. And finally, after all this stuff, you see that I'm coming to J2 times J integer, which means that I started with some reasonable description of second perturbation, and I can finally arrive that it is described on the language of phi. And here we wanted to check on the trivial example. If we get any advantage speaking on the language of phi theta, why? Because I worry about the value of scaling dimension. If scaling dimension is 100, it doesn't work in integer liquid because you compare it with 1 or 2. And look what was going on here. If I take this perturbation as the first one, I can define what I'm speaking about. And you see that this is indeed the description of this backscattering of 3 particles. 3 particles between different channels. If I translate this J and Q on the language of J1 integer, I obtain the following. I'm sorry, I cannot go there. And this is still 3 particles. Then I take the second perturbation. And the second perturbation is perturbation by, let's have a look, 5 particles. And I can easily check what is J2 integer, but I need J2 effective to get its contribution. So I'm just doing this procedure using these numbers. And this is what I'm getting. And it turns out that what was suggested to be described on the language of 5 particles of phi and theta, you have language of 18 particles being backscattered in some particular channel, which is already gave us some hope. And this is why I was presenting it all the time, that maybe still the description of phi theta is much better. Now, to be completely honest, I have to say that we are working about this so-called orthonormalization procedure, and it turns out that maybe we can live without it. And first, it was kind of disappointment because I cannot show you how our results is much better than the previous one. On the other hand, it turns out that hopefully it will give us an opportunity to describe indeed the variety of answers, because the answers on the language of phi are only squares in the numerator and squares in denominator. And it turns out that you can make more, but this I will leave, hopefully, for Igor's visit. So let us go back to the, can we still, just on the language of phi, describe what was observed? So the first number was 1/2, and I told you that how happy we were that we have this basic but 5-channel description, and it worked nicely. So this was the answer. Now was the question, can I, on the language of the same description, to find another even number, 1/6? And once again, it was a nice exercise on the level, okay, not of the third grade, maybe 5th grade of the basic school. What do you need to subtract from 1/2 in order to get 1/6? It is 1/3. So here you can call it fine-tuning or something, but lucky for us, those were the same numbers which were used by Shavit and Oregon in their paper. Remember, 3 and 1. So nevertheless, that I have now 5 channels, and I want to describe why I want to describe it on the same number of channels, because they were changing voltage and they were getting all these answers from the same experiment. So I don't know, on the one hand, you can say that changing voltage, they changed the number of channels, but it wasn't monotonic. So because from the very beginning, it was like 1 channel, then it was 5 channels, then it were 2 channels. So I don't know. So we suggested that what perturbation can we add to this basic one, which will collaborate with it. What does it mean collaborate? To be orthogonal and to be Haldane. Haldane is automatic here. When you are talking on the language of phi only, all perturbations are okay with Haldane. So it was easy to suggest that if I take perturbation which involves only 3 particles, you see that it is normal to this original perturbation. So I can calculate how much being stolen by this perturbation and subtract it from 1/2. And you see that this second subtraction was exactly 1/3. So you get 1/6. Once again, it gives you some hope that if 1 perturbation gives you 1/2 and 2 perturbations give you 1/6 and you observe it on the same experiment, maybe there is something here. So is it possible to describe all of them? It's easy to answer. In order to describe 1/2, you need just these perturbations. Trivial. 1/6 you describe with the help of 2 perturbations. 1 is the easiest one. If you have 5 channels, how many you have to close to get 1? You have to close 4. How you close 4 channels? You just make backscattering in 4 channels and you do not touch the 5th one. This is trivial. And indeed, it works. So once again, just 1 perturbation. But unfortunately, what was the easiest answer in the paper by Shavit? Because they have used 2 channels and they got the 3 and 1 immediately. Now you need to play in order to get 2/5. Once again, I can tell you, no, here we are coming back to 2 channels. So let's take 3 and 1 from Shavit paper and that's it. No, I wanted to make it 5 channels. This was already, let's say, fine-tuning. It turns out that you need 4 perturbations, which will collaborate, and they do collaborate. They all are orthogonal to each other. What was good about this, you see that, you see that they all have the same numbers, 3 and 1, as was in Shavit paper. So once again, some hope. Okay, I'm almost done. I'm coming to the next slide, which I promised you when you asked about the number of shells. This, it wasn't in the main paper, but we got all the papers by Pepper Group. And this was one of the numbers. I'm not trying to get all the knowledge from Mike Pepper, but we didn't get all of it. The idea was that this splittings mark that you now have 2 channels instead of 1. So if you calculate the number of peaks here, it is 5. Nothing more I can say.
Exactly is shown there. I don't know.
I even can tell you it is as a function of magnetic field. It's peak splitting.
Some
To be honest,
scattering experiments or something.
as I say, it's not a proof of my stock, so
Okay.
but at least there is a number 5 here. That's all I can say. So this is the paper which is mentioned. So you see, it's also not the main journal which they published. So this concludes my talk. And as I told you, I mean, just some days ago, we were seeing that we are completing it and closing everything. Now there is a huge amount of work to be done, to describe, to be accurate. So actually, my part about phi and theta, part of it will be reconsidered. No, Haldane criterion, the neutrality, everything, but orthogonality of perturbations, there is no need in such a words. If you are talking about perturbations which live in the same space as only J, yes, this is the idea of orthogonality. But if your perturbation is described on 2 languages, J and Q, phi and theta, then all you need is that you have a proper description of your system. And this is very interesting. And hopefully it will give us some more results. I just don't want even to talk about it because we are working on it, and I hope that maybe Igor will tell it when she comes here. So this concludes my talk, and so it's really interesting that you can, on one hand, why do you need larger liquidity if your K is equal to 1? But it turns out that still you can work on the language of multi-channel larger liquid. And you can present that, you can describe it on the language of intra and inter-channel backscattering processes. And you just subtract what was being get from your system, and you obtain the numbers of channels. Number 5 is really big, and maybe there will be some proof that we need 5 channels in order to get 1/2, because this is really a robust conductance. They observe it really good. And hopefully we will be able to describe also the relevant perturbations to produce for experimental evidence. Thank you very much for that.
Yeah, thank you, Victor, for this nice talk. We have time for questions. Yes, Henny.
I was wondering if there's some evidence, if you were to look at the noise, the shock noise in the system. And let me tell you something why I asked, because when we look at systems which have more than just one way to scatter, then it's actually important if these ways are orthogonal to each other. If they're not orthogonal to each other, the noise is enhanced. So in quantum optics, we have this number, it's called the Peterman. I was wondering, obviously, we know from noise measurements in these quantum Hall systems that we can get some information about the fractionalization, but maybe there's a bigger story behind this if you were to consider this.
I will only, but I will promise you, because we are in permanent contact with Pepper Group, Pepper and Kumar. These are the main figures. We probably ask them, because I understand what you're talking about, this famous Reznikov experiment about that you can observe fractional charge through the noise experiment. Yeah, maybe it could be great proof for it, but obviously they will not use analysis.
Maybe you can calculate it. So, let me ask another question, but very briefly. What is the role of spin?
No, okay. No, there is no. There is no spin polarization here. This is very thank you for asking because I was even pushed a little bit with this. This number is squared over 2h. It's not conductance per spin. It is real conductance. So spin doesn't play any.
So is it the magnetic field is so large?
No, there is no magnetic field at all. There was a magnetic field just to calculate this 5 number, but
It's an odd number of channels.
yeah, no, but this is in some sense it's unique because they really reproduce something fractional without.
Thanks.
Okay, more questions?
Let me just imagine that there's some experimental data which includes some details, information of the channels. That if I understand correctly, that from your talk, that to understand or analyze the experimental data, the new basis after the transformation probably a better or usual. Am I right?
You mean that it was possible in the experiment after part of it was localized to observe new channels? You see, okay, I mean, you know that there are some people like Jacobi in Harvard who can measure where exactly your current is flowing. So you know that he just moves a point above and it tells him where the current is flowing. And he was, for example, observing that sometimes quantum Hall effect takes place not only on the edges but inside. So maybe this would be a possible approach. So because in some sense, okay, let's put it this way: we start with no perturbations, so the data should show me that there is a number of channels. Then I don't know, I decrease temperature, might change something. And then the distribution of currents, you're absolutely right, should change somehow, but nothing more than that.
If I understand correctly, that you're some method that is introducing the new basis. That
Yes,
it's
but
possible.
you're absolutely right, but I don't have its position. It depends on the coordinate or something like this. This is just the description that you start with the basis of orthogonal channels, and then you rotate this basis, and in the new basis, part of the channels being localized, and you describe the rest.
But this is in principle possible even in the absence of the interaction. This is just one of the
Yes, the description of the system. You're absolutely right. Yes, it is possible.
Okay, more questions? Doesn't seem to be the case. Let me just add that Victor is here for roughly a month, so you can chat with him on channels and other things during this time.
So we will communicate for sure.
Okay, so let's thank Victor once again. Thank you.